A modern industrial gas turbine generates massive mechanical torque, heat, and vibration. To monitor this stress, sensors capture tens of thousands of data points. You would expect this volume of information to yield absolute clarity. Yet at the executive level, industrial leadership frequently finds itself arguing over basic operational realities. Consider a standard monthly review. The maintenance execution system reports an impressive 97% equipment availability. Right next to it, the enterprise financial system shows maintenance costs are up by 15%. These conflicting metrics create an operational blind spot. The available data shows the contradiction, but fails to explain the underlying cause of the divergence. Without a clear answer, organizations burn critical time debating whose spreadsheet is accurate, rather than investigating the physical performance of the equipment itself. When specialized databases are kept completely isolated from one another, they turn asset information into a liability. Establishing true operational visibility requires replacing these disconnected silos with a unified data architecture. The root of this conflict lies in how we view the software itself. Too often, organizations treat highly specialized database platforms as interchangeable, catch-all tools. Maintenance Information Management, or MIM, functions as an ecosystem of distinct, purpose-built databases. While operators interact with front-end applications, these databases are the actual engines underneath. They are the structures making complex reporting, historical analysis, and decision-making possible. Resolving these data conflicts requires a precise map of the jurisdictions within this ecosystem to identify exactly where the ground truth is formed. The bedrock principle of this architecture is strict specialization. At the base level, the CMMS handles execution. It answers, what work was done? Running parallel, the ERP manages budgeting to answer a different question, what did it cost? A financial system is engineered for accounting logic, making it inefficient for scheduling mechanical maintenance. Next, we add the asset performance management and process control systems. These platforms ingest condition monitoring and sensor data to build predictive models. Their job is to tell you what the asset is doing right now and calculate when it is mathematically likely to fail. When leadership forces one of these systems to adopt the jurisdiction of another, like trying to run reliability analytics directly out of a pure financial ERP, it degrades the structural integrity of both platforms. Maintaining strict boundaries is necessary, but leaving these platforms completely isolated slows down daily operations. It forces human workers into redundant manual data entry across multiple screens. This chart illustrates the interoperability layer. Specialized systems connect via a central sharing environment to synchronize outputs. For example, if an IoT sensor detects dangerous vibration on a pump, that data travels through the sharing layer to instantly trigger an inspection in the CMMS. Automating that specific data flow ensures immediate coordination of maintenance tasks. It eliminates manual intervention, drastically reducing the operational friction and administrative cost of the repair. Integration weaves siloed departments into a synchronized unit. But this speed relies on one assumption, that data flowing through the network is perfectly clean. Data does not move between databases by magic. It relies on vendor-defined structures, rigid communication protocols, and highly specific data codes. The weakest link is human input. When a rushing technician guesses which failure code to select from a drop-down menu, bad data enters the pipeline. From the CMMS, this corruption cascades through the interoperability layer, infecting the APM and the ERP. Once poor coding enters the ecosystem, management reports become immediately unreliable. Long-term trends mislead leadership, and expensive reliability analytics lose all credibility. Advanced integrated networks amplify the errors found in bad source data, mathematically spreading the corruption across the entire enterprise. Securing the architecture requires a final overarching layer, the Enterprise Data Warehouse, or EDW. The EDW is not an operational system. You cannot use it to schedule weekly maintenance, and a technician cannot use it to close a work order. Its specific function is to extract fragmented data from the CMMS, the ERP, and laboratory systems. It standardizes those inputs, strips away the conflicting codes, and stores the clean data historically for deep analysis. This solves the initial contradiction. By pulling the 97% availability metric from the CMMS and aligning it directly with the 15% cost spike from the ERP, The EDW merges them into a single cohesive narrative. It shows leadership exactly how expensive it was to achieve that high availability, revealing the correlation between cost and physical performance. This synthesized view is the single version of truth. This diagram illustrates how this entire software architecture maps directly onto the logical reality of physical asset management. The first pillar is the asset registry. By pulling specifications from engineering and supplier systems, it establishes an exact definition of what the physical asset actually is. The second pillar relies on the CMMS to track maintenance history and failure records. This establishes the operational reality, documenting exactly what work was executed and what the immediate result was. The third pillar takes that historical record and feeds it into the APM, along with expert recommendations. This step analyzes the past to project what you should do with the asset in the future, and precisely when you should do it. This logical flow takes raw physical sampling and historical failures and translates them structurally into proactive, predictive maintenance models. Operating this matrix successfully requires strict discipline. Organizations must protect data quality at the source layer, ensuring technician input is accurate to feed the rest of the ecosystem. It also requires abandoning the idea that a single monolithic database can effectively manage the complex, multi-departmental realities of an industrial facility. When executed correctly, a mature maintenance information management strategy results in perfectly synchronized, highly predictive, and reliable operational execution. By respecting the jurisdiction of specialized systems and synthesizing their data through an enterprise data warehouse, an enterprise stops arguing over conflicting spreadsheets and starts executing reliable physical performance.